Alright, in the last video, we did the divisibility rules for 2, 4, 5, 8, and 10. So we might as well cross them off to say we've done that. I also wanted to note that with the numbers 2, 4, and 8, well, 2 we had to check if the last digit was divisible by 2. 4 we had to check if the last 2 digits were divisible by 2. 8 we had to check if the last 3 digits were divisible by 2. So looking at this, you might be able to conjecture what the divisibility rule for, say, 16 would be, or 32, or any power of 2. 2 to some power k. K can be any number you like. How many digits of a number would you have to check? So think about that. You'll probably see that as a question on an assignment or something like that in the near future. Another quick reminder that we don't have a really nice rule for 7, nothing that's easy to prove anyway. But in this video, I'm going to show you the rules for 3 and 9 because they're basically the same. And then we might even do 11 either in this video or the next video. And 6, it's a little bit different to show that it works. The proof is a little bit different, but it's a nice easy rule, of course, because it's in some sense a combination of two things. Alright, so let's go ahead and let's talk about 3 and 9 first. Maybe let's do 9, I think. So let's go ahead and do 9. So again, this all has to do with place value. So I'm going to take that 4-digit number. Again, there's nothing special about 4 digits. That's just the case we're working with. This whole idea would work for any number of digits. I'm going to break this up into its expanded form, just like before. And if you notice here, none of these terms, we can say for sure, has a factor of 9. But think about 1,000, 100, and 10. Think about how close they are to a multiple of 9. So maybe pause the video now. I know it's kind of a nebulous question maybe, but think about how these relate to some multiple of 9. If there's a nice easy thing you can do to all of these numbers, and the same thing to make it a multiple of 9. Alright, now that we're back, well, hopefully you guys have seen that, hey, these are just one more than a bunch of 9s. So this is one more than 999. 999 is definitely divisible by 9, of course. 99 is, and 9 is. So we're just off by 1. So that's going to be a real key thing here. So maybe let's write 1,000 in terms of this 999 and then that 1 left over. So I'm going to write this as 999 plus 1 plus b times 99 plus 1 plus c times 9 plus 1. Maybe I'll put my multiplication symbol in there. It doesn't really matter, but just to keep it standard. Plus d. And actually I noticed something. I wrote a times here. I should really write a plus. So in this here, that should have been a plus. I had it as a times by mistake. So we know a bit of this stuff is divisible by 9 for sure. This bit, and this bit. So let's gather all that together so maybe we can apply Theorem 2, so the sum of those things. So we'll expand this out. And we get a times 999 plus a times 1, which is just a. So that's the first bracket here, a times 999, plus a times 1, which is just a, of course. Same thing here, b times 99 plus b times 1 plus c times 9 plus c times 1 plus d. Well, Theorem 1 now we can apply to all this stuff. So we'll apply Theorem 1. We know that all of those are divisible by 9, since 999, 99, and 9 are. Well, let's collect them together. Let's use the commutative and associative properties to move things around and group things, so we get all of that stuff together. So we have a times 999 plus b times 99 plus c times 9. We have that by Theorem 2 is definitely divisible by 9. And what do we have left? We have the other stuff. What do we have left? We have this a, b, c, and d. So we have this a plus b plus c plus d. And what is this? This is the sum of the digits. So this is what we need to check. So that's the idea. So we kind of break off this 1 from each of the powers of 10, and then the rest of it's divisible by 9. So then we just apply Theorems 1 and 2 after we gather up everything nicely like this, and the stuff that's left over, that's what we have to check. So let's go ahead and write that up. So this is the divisibility rule for 9. So 9 is a factor of the number a, b, c, d exactly when 9 is a factor of the sum of the digits. So let's go ahead and just write this down in a nice proof. The idea is all up here. All right, so we know, so let's note that 9's a factor of 999, 9's a factor of 99, and 9's a factor of 9. Of course it is. You can check these. If you divide 999 divided by 9, you're going to get 111. I think it's pretty obvious that this holds, and everything divides itself anyway. So these are pretty obvious. Okay. So let's go ahead. So by Theorem 1, or let's say, first of all, maybe before that, let's say rewrite a times 1,000 plus b times 100 plus c times 10 plus d as, let's just write it exactly in this form. Here are the steps. We know how to do it, so let's just say we can do that. So it's going to be a times 999 plus b times 99 plus c times 9 plus d, sorry, not plus d. I'm getting carried away here. Plus, then we have the stuff left over, a plus b plus c plus d. And again, we're going to bracket it like that. And then we can say, basically, the same as what we did for the proofs for 2, 5, 10, 4, and 8. So by Theorem 1, we know that 9 is a factor of a times 999. That's a multiple of 999, so it's going to be a factor. 9 is a factor of b times 99, and 9 is a factor of c times 9. And by Theorem 2, we know it's a factor of the sum of those guys. 9's a factor of the sum. A times 999 plus B times 99 plus C times 9. Again, if you're not following any applications of the theorems, it's always a good idea to pause the video and open up the previous video that we started with talking about the 3 theorems, and make sure that those theorems make sense so you can see why we can apply Theorem 2 to this sum. Okay, let's scroll and make some room. Alright, let's go ahead. So now assume that 9 is indeed a factor of the sum of those 3 digits. So we checked, and it is. Well, then we can apply Theorem 2. So then, by Theorem 2, we get that 9 is a factor of A times 999 plus B times 99 plus C times 9. So that's the stuff we know for sure is divisible by 9, and then the stuff we assumed, the sum of the digits, that's divisible by 9. So 9's a factor of that. And, well, let's just write, so 9 must be a factor of the number written in its usual form. Because all we're doing here, we didn't do anything to change the number. It's the same number, just arranged differently. It's kind of no longer in base 10. It's no longer in its blocks. We broke off one block from every block that we have and gathered them all together. So every block, you can draw some blocks out if that helps you, and see, take off a 1 from each of the blocks, from each 10, 100, and 1,000 block that you draw, and the ones that you gather together, those ones blocks, here they are, here. That's what's kind of happening. So 9 is a factor of the number that we started with, because this is the number that we started with. Okay, and now let's assume that 9 isn't a factor of the sum of the digits. Let me make just a little more room here. Then Theorem 3 tells us we know 9 isn't a factor of our number. Here's our number here. Remember, we know this bit is definitely divisible by 9 by Theorem 2, and this we're assuming isn't, so Theorem 3 tells us that whatever remainder this has here, when we add these numbers together, that remainder carries along. So we can say that 9 isn't a factor of our number written in its kind of regular form. There we go. And we're done. So you can see why place value is important. Having an idea of place value allows us to figure this out. Okay. So let's do a quick example. So, in fact, let's find a k such that 9 is a factor of the number 92,370,920. Okay, so this k is a digit. It's the thousands digit. All right, so remember, this says that the sum of the digits has to be divisible by 9. It has to have a factor of 9. So pause the video now and see if you can figure this out. Okay, Well, we need to check if the sum of the digits has a factor of 9. So, let's do it. Let's take the sum of the digits. We don't know one of them. It's an unknown, but that's okay. So, we have 9 plus 2 plus 3 plus 7 plus k plus 9 plus 2 plus 0. Let's add these up. So we get 9 plus 2 is 11, 14, 21. We'll deal with the k later. It'll just be plus k. So 21, 30, 32, and 0 is 32 as well. So we get 32 plus k. And remember, k is a digit. So k is going to be a number 1, 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. And then, well, with all of these you can check, but the only one that gives you a multiple of 9 is if k is 4. So, let's say if k equals 4, then 32 plus 4 equals 36. And 9 is a factor of 36. And thus, nine's a factor of our original number. 92,374,920. And you could check for any other k. 9 isn't a factor of that. 370k 920. So that's cool. That's how the rule for 9 works. Let me scroll back up. And think about the rule for 3 here. So, basically, look at this and ask yourself if 3 is a factor of 999, 99, and 9, and if it is, then you can just modify this proof by changing all of these 9s to 3s, and you're good to go. And in fact, of course it is. So, the divisibility rule for 3 is the same. If the sum of the digits is divisible by 3, then your number is divisible by 3, and if it isn't, then your number isn't. So I'm going to pause the video just like I did before. I'm going to erase all of these 9s here and replace them with 3s. So there we go. The proof is literally the exact same, and for the exact same reason that the proof for 2 and 5 was. Those kind of factors that we chose were divisible by, are divisible by 9 and 3, just like they were divisible by 2 and 5, and 10 for that matter. So the same idea applies, which is pretty cool. So the sum of the digits, if it is divisible by 3, then the number is divisible by 3. If it isn't, then the number isn't. So we only have 2 rules left, 6 and 11. So let's talk about those. So let's talk about the divisibility rule for 6. In fact, I don't think we'll go ahead and prove this. I will just tell you it, and then we can use it. So basically, all it's saying, the divisibility rule for 6, is just combining the rules for 2 and 3. So a number is divisible by 6 exactly when it's divisible by 2, and it's divisible by 3. But I do want to talk about one kind of thing here. So remember, this is a biconditional. So we can write it as 2 if-then statements. So we can say, if 2 is a factor of our number and 3 is a factor of our number, then 6 is a factor of our number. But we can also negate both the if and then parts for the other direction. So if 2 isn't a factor or 3 isn't a factor. Because remember, if we're negating something with an and, we negate both parts, and we change the and to an or. So negating this becomes 2 isn't a factor of A, B, C, D, 3 isn't a factor of A, B, C, D, and the and flips to an or. But basically, what it's saying is you just combine the rules for 2 and 3. When both of them hold, then your number is divisible by 6. And the divisibility rule for 11, again, I'm not going to prove it. It's kind of interesting. So 11 is a factor of your number. Exactly when? 11 is a factor of the alternating sum. So you start with your a positive digit, then you subtract a digit, then you add a digit, then you subtract a digit. So this is the alternating, it's called the alternating sum of the digits. So if you're interested in why these are true, you should be able to read them in your textbook, or even if you just Google them, the proofs should be out there. They're not too hard to understand, but just in the interests of time, I won't prove these because we did a whole bunch of proofs so far. These ones are just slightly more complicated, but not too much more complicated. Anyway, let's check. Let's do an example to see how these rules work. So, let's pick a number. So let n be the number 32,971,692. So let's see if 6 is a factor of that. That's going to be the first question. And the second question is going to be, is 11 a factor of that? All right. So maybe pause the video and see if you can figure this out. Okay, now that we're back, let's have a look. So we need to check if the divisibility rules for 2 and 3 hold. So let's do the first part here. So 2 is a factor of the last digit. 2, of course, the last digit is even. So we know 2 is a factor of our entire number, and 32,971,692. Let's check 3. Is 3 a factor? So is 3 a factor of n? Let's see. So we'll add the digits together. Remember, our rule for 3 says if the sum of the digits has a factor of 3, then the number has a factor of 3. So let's check. Is 3 a factor of 3 plus 2 plus 9 plus 7 plus 1 plus 6 plus 9 plus 2? And we're seeing if 3 is a factor of, well, let's kind of use the associative and commutative properties in our head to kind of look for tens. So that'll help us a little bit. So, and I'll just cross them out as we go. 9 plus 1 is 10. 7 plus 3 is 10, so now that's 20. 6 plus 2 plus 2 is 10, that's 30. And then we're just left with this 9, 39. So is 3 a factor of 39? Well, that's pretty easy to see it is, of course, but if you weren't sure, you could just do the rule again. So you do, is 3 a factor of 3 plus 9? And you'd get, is 3 a factor of 12? And keep going like that. Of course it is. 3 is a factor of 1 plus 2. 3 is a factor of 3. So we're good to go. But if you're happy that 3 is a factor of 39, you can stop there. And we can say, well, 3 is indeed a factor of 39. So 6 is a factor of our number, since, 3 is a factor of 39, which means that 3 is a factor of n. So since 2 is a factor of n, and 3 is a factor of n, 6 is a factor of n. Remember, we need both to be true. If we got some number like 40 here instead of 39, say if this was 792 instead of 692, so we had an extra number here, then this wouldn't hold, so your number wouldn't be divisible by 6. Now let's do the rule for 11. So here we go. We need to do the alternating sum of the digits. So let's go ahead. Is 11 a factor of? So plus 3 minus 2 plus 9 minus 7 plus 1 minus 6 plus 9 minus 2. So, and it doesn't matter if you start with negative or positive, as long as they alternate, you're good to go. So, what is this going to be? I'll just do this from left to right. 3 minus 2 is 1, plus 9 is 10, minus 7 is 3. 4 minus 2, 7, 5. So this is 5. And 11, is 11 a factor of 5? It is not. 11's not a factor of 5, so 11 is not a factor of 32 million, etc. So that's how the rule for 11 works. So I want to make a couple of notes about the rule for 11. So, common mistakes students make. So if they get a sum of 1, remember 11 isn't a factor of 1. 1's a factor of 11. But if you get a sum of 1, then your number isn't divisible. The second note I want to make is that if you get a sum of 0, remember, everything's a factor of 0. So you're good to go if you get a sum of 0. You can imagine a number like 11 is definitely a factor of 77. 11 times 7 is 77. If you apply our test, is 11 a factor of 7 minus 7, the alternating sum of those digits, which is 0. And 11 is a factor of 0. 11 is a factor of 77. So hopefully you can kind of see that there. And the other thing I want to note is that you can either have positive or negative a multiple of 11. So sometimes when you do this sum, you'll end up with a negative number. Whatever, don't worry about the negative, just focus on the positive bit of the number. It doesn't matter if it's plus or minus. And here's a little challenge exercise for you guys. So, show that you can't make a number divisible by 11 by arranging or rearranging the digits 1, 2, 3, 4, 5. So you have a 5-digit number here. Whatever order you have these in, it will never be divisible by 11. See if you can figure that out. It is kind of challenging to think about. I'll give you some hints. Remember, you have to have an alternating sum of the digits, tells you if it's divisible by 11. Think about what the biggest sum you can get is. So that's the first hint I want to give you. And the second hint I want to give you is think about if the alternating sum is going to be odd or even. So those two hints there should give you a good clue about how to show that you can never make a 5-digit number just with these digits by rearranging them that's divisible by 11.